Right. Yeah. Thank you very much for the introduction. Yes, it's my great pleasure to speak here. I mean, it's a great honor to get this opportunity. Thank you a lot. Thanks to the organizers. So I'm a PhD student at TU Wien, and today I'm going to talk about work that I did together with Stéphane Detournay, Wout, Merbis, and Seng. So our goal in this project was to reproduce the entropy of certain three-dimensional spacetimes that were flat spacetimes through a microscopic derivation. And the plan of this talk will be as follows. I will start with a motivation and historic overview of how the entropy of the three-dimensional BTC black hole was reproduced using a conformal field theory derivation. Then I will discuss a new class of field theories, which are called warp conformal field theories. And then I will talk about the spacetimes that we studied, these warp flat spacetimes, as I said before. I will talk about the causal analysis, and then I will end with how their entropy can be reproduced using a warp conformal field theory. It's known since the 70s, after the seminal works of Hawking, Bekenstein, Bardeen, and Carter, that black holes behave like thermodynamic systems in the sense that they have a temperature and they have a very large entropy. And now, one question that one can pose is, can this entropy be derived through a microscopic derivation? And to answer this question, it's often useful to consider toy models. And one such toy model is 3D Einstein gravity. In 3D Einstein gravity, there are no gravitational waves, and the curvature is constant for all solutions of the Einstein's equations. In particular, the Riemann tensor looks like this for all solutions of the Einstein's equation. So locally, 3D Einstein gravity seems trivial. However, global properties allow for interesting solutions. And in particular, it was shown that for negative cosmological constant, black hole solutions exist in Einstein gravity. In 1992, Bagnados, Teitelbaum, and Zanelli found a two-parameter family of solutions that you see here. And here the two parameters are M and J, and L just comes in over the fact that this metric here solves Einstein's integration with negative cosmological constant, which is -1 over L squared. And for M greater than 0 and J being smaller or equal to M times L, this metric up here describes a black hole, which is very surprising because it has a constant curvature, and usually we're used to black holes having a curvature singularity. But this is, of course, not the case in 3D. Nevertheless, the solution describes a black hole. And the reason for this is because it has the defining feature of a black hole, namely a black hole region, as can be seen from inspection of this causal diagram. So the BTC black hole and ADS3 are locally the same as we said before. And in particular, the BTC black hole can be obtained as a quotient of ADS3. Braun and Hainaut studied in 1986 boundary conditions for asymptotically ADS3 spacetimes. And what they found is that there are infinitely many Killing vectors, leaving these boundary conditions invariant, and they have infinitely many associated charges whose Poisson brackets span 2 copies of the Virasoro algebra. And nowadays, this is often interpreted as a precursor of the ADS3 CFD2 correspondence, which conjectures that quantum gravity on ADS3 spacetimes is dual to a two-dimensional conformal field theory. And Andrew Strominger had a famous paper in 1997 where he used the analysis of Braun and Hainaut to show that the entropy of the BTC black hole precisely matches the Cardy formula. And the Cardy formula is a formula that can be intrinsically derived from a two-dimensional conformal field theory. And hence, in some sense, this gives some microscopic interpretation, so to speak, because you can reproduce the entropy of the BTC black hole through accounting, but it is accounting in a two-dimensional conformal field theory. And since then, of course, it has inspired a lot of work in this direction, and people have worked on asymptotic symmetries, and they have also worked on matching the entropy of certain spacetimes or certain black holes to an entropy on the field theory side. But most of these analyses are actually use the original analysis performed by Brown and No, and they usually involve ADS3 or the isometries of ADS3, SL2R plus SL2R. And in this talk, I want to provide an example of a matching for spacetimes which do not fall into this category. And work on asymptotic symmetries in general and in this direction has also led to the discovery of many new field theories. And one of these new field theories are so-called warp conformal field theories, whose symmetry algebra you see here. So they also have an infinite dimensional symmetry algebra, and they admit up to 3 distinct non-trivial central extensions, C, kappa, and K that you see here. And one nice way to understand warp conformal field theories is the following. Polchinski showed in 1987 that the symmetries of any 2D local unitary translation and scale invariant quantum field theory with a discrete spectrum of the dilatation operator enhance the 2 copies of the Virasoro algebra. And Andrew Strominger and Diego Hoffman considered something similar in 2011. They considered a quantum field theory with the same assumptions, but with scale invariance only in one direction. And what they found is that also in this case, you have symmetry enhancement. And in fact, there are 2 minimal options for the enhanced symmetry algebra that you get. You either get the symmetry algebra of a warp CFT or you get the symmetry algebra of a CFT. And you can get back to just getting 2 copies of the Virasoro algebra, which is the symmetry algebra of a CFT, by adding back the scaling in the second direction. But similarly, you can single out the warp CFT by adding a boost. Now, in our work, we were focused on certain 3-dimensional spacetimes, dubbed warp flat spacetimes. And here you see the metric of warp flat space. And the reason why it's called like this is because it's a vibration over 2-dimensional flat space. And this is a 3-dimensional spacetime, which is a solution to topologically massive gravity with positive cosmological constant. And here you see the equations of TMG. Lambda is the cosmological constant, mu is this coupling to the Cotton tensor. And this metric up here has constant positive scalar curvature, but it's not maximally symmetric. In particular, it has 4 killing vectors, and the algebra that they span is the centrally extended to the Poincaré algebra that you see here. So this would be the translations, T0 and T1, K would be the central extension, and J would be the boost. And it's kind of curious because we have positive cosmological constant, but the isometries that we have are span the algebra of 2D flat space plus a central extension. And now, so these spacetimes already appeared in literature, and Vikula 1 quotient appears, and it's the quotient along K, so it's a quotient along a shift, appears as the near horizon geometry of Cardy-Zeta black holes at fixed azimuthal angle in the limit where the outer, the inner, and the cosmological horizon coincide. But in our work, we were interested in a different quotient. In particular, we were interested in the following quotient, which is a quotient along a boost, a combination of a boost and a shift, and psi and omega are just 2 constants, which are introduced when performing this quotient. And these quotients were claimed to be black holes in the regime where psi plus 2 omega are greater than 0. And this is work that goes back to Musa and collaborators in 2008. And this was also originally the reason why we got interested in these spacetimes, because they were claimed to be black holes and they had these very funny isometries. And one of the question that we try to answer in this in this project was, are these warp flat quotients black holes? And to answer this question, we used projection diagrams, which were developed by Piotr, Christa Oels, and Sebastian Sipka in 2012. And these projection diagrams are useful to depict non-block diagonal metrics with 2D diagrams. And while they are similar to conformal Carter-Penrose diagrams, there is a crucial difference, namely that a projection diagram is not necessarily a slice of spacetime. Now let me give you the formal definition. This was given in the paper by Piotr Krusche and his collaborators. So let MG be some smooth spacetime. Then a projection diagram is a pair pi u, where pi is a map from M to W. W is a subset of R11, and this map is continuous and it's differentiable on an open dense set. And U is a subset of M. This is an open set on which pi is a smooth submersion such that the following two conditions hold. That every smooth time-like curve sigma in pi of u is the projection of a smooth time-like curve gamma in u, and that the image of every smooth time-like curve gamma in u is a time-like curve in R11. So in particular, every time-like curve that you have in u gets mapped to a time-like curve in R11, and to each time-like curve in pi of u, there exists at least one time-like curve in u. And these conditions 1 and 2 ensure that causal relations on pi of u reflect as accurately as possible causal relations on u. Under the map pi, causal curves are mapped to causal curves, but for instance, many space-like or null curves become null or time-like. And another point is maybe that as it's possible to project in different ways, different projection diagrams may carry different information about the causal structure. So okay, let's get back to the question. So we wanted to answer this question whether the warp flat quotients are black holes. And so these are the projection diagrams, and the way that we obtained them was that we projected out the direction of identification, which is the most natural thing to do, I would say. And depending on the regime of the parameters that were introduced in performing this quotient, the spacetime either looks, the projection diagram of the spacetime either looks like the left picture or like the right picture. And the shaded regions in the right picture are the region that must be excluded from the diagram, because in this region, the vector along which we identify becomes time-like, which leads to the appearance of closed time-like curves. And the dashed lines denote the location of the Killing horizon that was claimed to be a black hole horizon in the paper I just cited before. And one can show that in both cases, the spacetime is not a black hole. And what we furthermore did in this paper was we have this Killing horizon, and we associate a Hawking temperature and entropy to it. And here the entropy is defined to be the Noether charge associated to the horizon Killing vector field. And in terms of mass and angular momentum, this entropy looks like this, where m is the mass and j is the angular momentum. And what we did for these spacetimes was we performed an asymptotic symmetry analysis and found that the asymptotic symmetries match the symmetries of a warped conformal field theory. And lastly, what we did was we showed that the gravitational entropy precisely fits the entropy that can be derived from a warped CFD. Well, thank you very much for your time and attention. And thanks to the organizers again.
Thank you very much for the nice and concisive talk. You stayed perfectly in time. We still have some minutes for questions. So questions or comments, please.
May I have a question about this projection from upper space to this two-dimensional one? You said that the time-like curves are projected on time-like curves. What about cones, local cones? How do they project null cones in this general setup?
Well,
maybe I can answer this.
Yes.
Yes. So of course, null cone is a limit of time. So null curves are limits of time-like curves. So if you have this control on the time-like ones, you get the causal ones by limits, by taking limits. So the only thing which probably in this definition might not work is that some null curves might not come from null curves in space-time, right? So I mean, in this definition, you could write a similar definition using causal, right? That nothing would prevent you to do it. But certainly the projection of null curves would be a null curve.
Ah, okay, thanks. No.
Raphaela, may I ask a question?
Sure.
Yeah.
So one can associate a temperature to a killing horizon, and but physically one thinks that this really should be associated with event horizons, right? And in this case, killing horizons are not event horizons. So how should one interpret this temperature now?
Of course, it's a very good comment. So of course, in the case of black holes, we precisely, I mean, we have this analogy, as you well know, I mean, to the laws of thermodynamics. I mean, that was found, and then what people have been doing is to extend somehow what we know from black holes also to cosmological horizons. The question of how well this really describes the thermodynamic entropy, I mean, it's not as clear as with black holes.
Maybe
so
I can comment
nice
on this. If you think about, so to say, accelerated observers in flat space, there is also this Unruh temperature associated with this, and they also have, so to say, a killing horizon. It's so to say the killing horizon for the boost vector fields.
Right. That's true. Yeah.
Okay.
So from your point of view, Herbert, the killing horizon would be actually the important thing.
Well, I mean, it works also in flat space. So you don't have a horizon in flat space, and you can have an accelerated observer that moves with respect to the Minkowski vacuum, but respect to a different vacuum, the Unruh vacuum. And one with respect to the other appears like a coherent state, if you want to. So in this sense, you can assign a temperature. It's not only a formal temperature in the sense that you read this like, let's say, the first law of thermodynamics, and then say, okay, one thing has to be the temperature, the other thing has to be the entropy. So there is sort of a physical interpretation.
Raphaela, do you think you could show your projection diagrams again?
Sure.
Yeah, so I think one of my problems when I see this is that, of course, normally when you want to do things, you want a globally hyperbolic space-times with Cauchy surfaces. And so the domain of outer communication in the space-time, which if you just took the one quarter, take the right picture, take the right quarter of this picture, right?
Yeah,
and this is not globally. Now the right one? Yeah, yes, the other one.
Okay, sorry, this one. Yeah.
My right, yeah. then this thing is not globally hyperbolic, right? Because of these causal curves which are there. So the projection diagram fails, but it's not that it has a gap, but this gap is real, right? So the gap comes from the fact that there are closed time-like curves in the space-time. Right. So it's hard to do any reasonable field theory on this thing which has not globally hyperbolic, right? And that's why as you just completely agree with you, this is not a black hole space-time because it doesn't have good black hole properties. Right?
But in some sense, I mean, so I mean, what I can say, I mean, is this is at least in 3D, it's quite standard, because in what you actually have for the BDC black hole, I mean, you also do identification along the orbits of a killing vector, and what you also get in the case of the BDC black hole is you get a region where there are closed time-like curves.
But normally these regions are beyond event horizons, right? So that's the point, right? So you have
right, but if I cut
here it's not, right?
But if I cut the space-time off, yeah, right. But that's true.
If you cut this away, then you'll get a boundary value problem rather than a normal, yeah, scry and stuff like that. And then all these notions of black hole just are completely different.
No, I mean this is for sure not a black hole. I mean,
right? Yeah, we agree with this, but I just wanted to point out that this is even more singular than not a black hole.
What I can say is, I mean, there are actually solutions whose causal diagram precisely looks like this. So these are referred to as flat space cosmologies. They are quite studied in 3D, and the way you obtain them is you get them as a limit from the BTC when you take the cosmological constant to 0. So in 3D, I mean, for 3D Einstein gravity, you only have black holes for negative cosmological constant, and it's shown that you cannot have black holes in 3D Einstein gravity for positive or null cosmological constant. But what people have been studying are these so-called flat space cosmologies, which would look precisely like this, namely you have this closed time-like curves, you cut the space-time off, and what you end up with is the singularity somehow. Mm-hmm. I mean, the place where this closed time-like curves start to appear.
Thank you.
Okay. Further questions or comments? If not, then I would think we should continue on. And